Mercury is the closest planet to the Sun. Most people picture a small, hot rock and move on. They are wrong in almost every way that matters. Mercury is not simply hot. It is one of the most operationally punishing destinations in the entire solar system. Getting there requires more energy than reaching Saturn. Surviving there means enduring temperature swings of nearly 600 degrees in a single day. And leaving may be the hardest part of all. The Sun's gravity turns every return trajectory into a fuel problem that no existing or planned spacecraft can solve with a crew on board. Tonight, we are going to show you why anyone who goes to Mercury will never come back. Not because Mercury kills you instantly, because it traps you completely. If you enjoy science that actually changes how you see the solar system, hit like and subscribe. We dig into the real physics behind the places most people never think twice about. Are you comfortable? Now, let's begin. Ask someone to name the planets, and Mercury barely registers. It is the small one, the one near the Sun, the one nobody talks about. In classrooms, it gets a single sentence. In documentaries, it earns a flyover shot before the camera moves on to Mars or Jupiter or Saturn with its rings. Mercury is the planet people skip. And that instinct, that casual dismissal, is one of the most dangerous misconceptions in all of planetary science. Because Mercury is not what you think it is. Most people carry a mental image of Mercury that goes something like this. A small, grey, cratered ball sitting close to the Sun, hot, barren, unremarkable, essentially the Moon, but closer to a star. If you push them further, they might guess it is the hottest planet. It is not. That title belongs to Venus, whose thick atmosphere traps heat far more effectively than Mercury's nearly non-existent one. They might assume it is the easiest inner planet to reach, since it is closer to the Sun than Earth. It is not. It is the hardest. They might imagine that getting there is simply a matter of pointing a spacecraft sunward and letting gravity do the work. That is not just wrong, it is the opposite of how orbital mechanics works. And that misunderstanding, the idea that falling toward the Sun means falling toward Mercury, is where the real danger begins. Because everything about a human mission to Mercury starts with a problem most people do not even know exists. Getting to Mercury is harder than getting to any other planet in the solar system. That sentence sounds impossible. Mercury is right there. On a diagram of the solar system, it sits closer to Earth than Jupiter, Saturn, Uranus, or Neptune. Closer than Pluto, which is not even classified as a planet anymore. In raw distance, Mercury can approach Earth to within roughly 77 million kilometers during favorable alignments. Mars, at its closest, comes within about 55 million kilometers. So, the distances are comparable. Mercury is not some unreachably distant world hiding at the edge of the solar system. It is a neighbor. And yet reaching it in any controlled, practical way requires more energy than flying to Saturn, more energy than reaching Jupiter, more energy, according to the European Space Agency, than sending a spacecraft all the way to Pluto. That fact alone should stop you. Let it settle for a moment. Pluto orbits at an average distance of roughly 6 billion kilometers from the Sun. Mercury orbits at roughly 58 million kilometers. Pluto is more than 100 times farther away. And yet parking a spacecraft in orbit around Mercury demands more total velocity change than doing the same thing at Pluto. The reason comes down to one force that dominates everything in the inner solar system: gravity. Not Mercury's gravity, the Sun's. Here is the part that most people get backwards. When you launch a spacecraft from Earth toward the inner solar system, you are not speeding up toward the Sun. You are slowing down. Earth orbits the Sun at roughly 30 kilometers per second. That orbital velocity is what keeps Earth from falling inward. It is a balance between the pull of gravity and the momentum of the planet's motion around its orbit. To move closer to the Sun, a spacecraft must shed some of that velocity. It has to slow down relative to the Sun so that its orbit drops inward. The less velocity it has, the closer to the Sun it falls. In principle, this sounds manageable. Fire your engines in the direction opposite your orbital motion, lose some speed, and your orbit contracts. But the Sun's gravity does not cooperate politely with this plan. As the spacecraft moves closer to the Sun's gravitational pull accelerates it. The spacecraft speeds up as it falls inward. By the time it reaches Mercury's orbital distance, it is moving far faster than Mercury itself, and that speed is the entire problem. Think of it this way. Imagine you are standing at the top of an enormously steep hill. At the bottom of that hill, on a narrow ledge, there is a small platform moving sideways at high speed. Your job is not just to reach the bottom. Your job is to land on that platform and match its speed exactly. If you simply let yourself fall, you will arrive at the bottom, moving far too fast and in the wrong direction. You will overshoot the platform entirely and continue falling past it, deeper into the valley below. To land on the platform, you must somehow slow yourself during the descent, cancelling the speed the hill's slope keeps adding to you. Every meter you fall, the hill makes you faster. Every meter you fall, you need to burn more energy to counteract that acceleration. And the platform itself is moving at a velocity that is extraordinarily difficult to match from above. That is Mercury. The hill is the Sun's gravity well. The platform is Mercury, hurtling along its orbit at up to 59 kilometers per second at perihelion. And the valley beyond it is the Sun itself, pulling everything that gets close into an ever faster descent. A spacecraft approaching Mercury from Earth's orbit does not gently drift into the planet's neighborhood. It screams through it, accelerated by the Sun's gravity to velocities that make orbital capture almost impossible without massive deceleration. The Sun is not helping you reach Mercury. The Sun is the obstacle. It keeps adding speed that you must subtract over and over, burning fuel or surrendering years to gravity assists, just to arrive at Mercury slowly enough to stay. Mercury orbits the Sun at an average velocity of roughly 47 kilometers per second. At perihelion, the closest point in its orbit to the Sun, Mercury moves even faster, reaching approximately 59 kilometers per second. That makes it the fastest planet in the solar system. A spacecraft arriving from Earth's orbit, falling inward under the Sun's gravity, will be moving at a velocity that does not match Mercury's. The mismatch is enormous. To enter orbit around Mercury, the spacecraft must decelerate massively. It must burn fuel or use some other method to shed velocity until it is moving slowly enough relative to Mercury for the planet's weak gravity to capture it. And Mercury's gravity is weak. The planet has only about 38% of Earth's surface gravity. Its sphere of gravitational influence, the region of space where Mercury's gravity dominates over the Sun's, is tiny. A spacecraft screaming past at high velocity relative to Mercury has an extremely narrow window in which capture is even theoretically possible. Miss that window by a small margin and you fly past. Overshoot it and you risk being pulled further sunward. The margin for error is razor thin and the energy cost to hit it is staggering. In astrodynamics, the standard measure of mission difficulty is called delta V. It represents the total change in velocity a spacecraft must achieve across all phases of a mission, from launch to orbit insertion and, if applicable, landing and return. Delta V is the currency of space travel. Every maneuver costs delta V. Every kilogram of payload increases the fuel needed to achieve that delta V. And the delta V budget for reaching Mercury orbit from Earth is among the highest in the entire solar system. A direct Hohmann transfer orbit from Earth to Mercury, the simplest two-burn trajectory, would require a delta V so large that no chemical rocket in existence could carry enough fuel to achieve it while also carrying meaningful payload. The numbers are punishing. The velocity changes needed to drop from Earth's orbit to Mercury's orbit and then match Mercury's velocity for orbital insertion add up to a figure that exceeds what is needed for missions to the outer solar system. This is not intuitive. It feels like it should be easier to go inward than outward. But the Sun's gravity well is not symmetric in terms of mission energy. Going outward, you add velocity and coast. Going inward, you subtract velocity while the Sun keeps adding it back. You are fighting the most powerful gravitational source in the solar system the entire way. And when you arrive, you must fight it again to slow down enough to stay. This is why every mission that has ever reached Mercury has relied on gravity assists, not as a convenience, as a necessity. Gravity assists are the only practical way to bleed off the enormous velocity that accumulates when a spacecraft falls toward the inner solar system. The technique works by flying a spacecraft close to a planet and using that planet's gravity to alter the spacecraft's speed and direction. Depending on the geometry of the flyby, the spacecraft can gain or lose velocity relative to the Sun. For Mercury missions, the objective is to lose velocity, repeatedly, over years. Consider the history. Mariner 10, launched in 1973, was the first spacecraft to visit Mercury. It used a single gravity assist at Venus to alter its trajectory and made 3 flybys of Mercury in 1974 and 1975. But Mariner 10 never entered orbit. It flew past Mercury, gathered data during each brief encounter, and continued on its heliocentric orbit. The reason it never orbited was simple. It could not slow down enough. The technology and fuel budget of the era made orbital insertion at Mercury impossible. Mariner 10 gave humanity its first close look at Mercury, but it was a glancing look. Brief passes at high speed with no ability to linger. It took more than 30 years before anyone managed to put a spacecraft into orbit around Mercury. NASA's Messenger mission launched in 2004. It did not arrive at Mercury orbit until 2011, 7 years of flight. During that time, Messenger performed 1 gravity assist at Earth, 2 at Venus, and 3 at Mercury itself. 6 planetary flybys across 7 years just to shed enough velocity to enter orbit around the smallest planet in the inner solar system. And even then, the orbit was highly elliptical. Messenger swung as close as 200 kilometers to the surface and as far as 15,000 kilometers away every 12 hours. That extreme orbit was not a design preference, it was a thermal survival strategy. The spacecraft could only endure close passes for brief periods before needing to retreat to cooler altitudes away from the broiling surface and the intense reflected radiation. Messenger's orbit insertion burn. The engine firing that finally captured it into Mercury orbit required a delta V of roughly 0.9 kilometers per second. That sounds modest until you realize it came at the end of a 7-year series of precisely calculated gravity assists that had already removed the vast majority of the excess velocity. Without those assists, the insertion burn alone would have needed to be many times larger. Impossibly larger for the spacecraft's fuel capacity. Now consider BepiColombo, the joint European and Japanese mission currently approaching Mercury. BepiColombo launched in October of 2018. It performed 1 flyby of Earth, 2 of Venus, and 6 of Mercury. 9 gravity assists in total. It has been traveling for nearly 8 years, covering approximately 9 billion kilometers, a distance far greater than the straight-line distance to Mercury, looping repeatedly through the inner solar system to gradually slow itself down. And even with all of that, even with the most advanced ion propulsion system ever flown on an interplanetary mission, BepiColombo encountered problems. In 2024, engineers discovered that the spacecraft's ion thrusters could not operate at full power due to unexpected electrical currents between the solar arrays and the power distribution system. The reduced thrust meant the original arrival date of December 2025 was no longer achievable. A revised trajectory was calculated, adding 11 months to the mission and pushing orbit insertion to November 2026. The spacecraft completed its sixth and final Mercury flyby in January 2025 and is now on its final approach. That is what it takes to send a robotic probe to Mercury. No crew, no life support, no return trip. Just a compact instrument package, and it still requires nearly a decade of flight, 9 gravity assists, advanced ion propulsion, and a mission budget exceeding $1.8 billion. Now hold that reality in your mind and ask the question that this entire story is building toward. What would it take to send humans? The answer begins with a word that appears in almost every technical discussion of crewed interplanetary missions. Consumables, food, water, oxygen. A crew needs all of these, and they need them continuously. Every additional day of flight time adds mass to the spacecraft. Mass that must be launched from Earth, accelerated, decelerated, and managed across the entire mission. A 7-year flight to Mercury is not an option for a crewed spacecraft. The crew would run out of everything long before arrival. Life support systems can recycle some consumables, but not indefinitely, and not without significant mass and power overhead of their own. So a crewed Mercury mission would need a much faster trajectory. Faster means higher thrust means more fuel means more mass means even more fuel to move that mass. This is the tyranny of the rocket equation, and it is merciless. Every kilogram you add to the payload requires exponentially more fuel to deliver it to the destination. For a destination like Mercury, where the delta-V budget is already among the highest in the solar system, the equation spirals out of control quickly. To appreciate just how quickly, consider some real numbers. The International Space Station has a mass of roughly 420 metric tons. It orbits Earth at an altitude of roughly 400 kilometers. It has never left low Earth orbit and was never designed to. It was assembled over more than a decade using dozens of launches. Now imagine a crewed Mercury vehicle. It would need pressurized living space for a crew of at least 3 to 6 people across a mission lasting at minimum a year and possibly several years. It would need life support systems capable of recycling air and water at high reliability. It would need radiation shielding substantial enough to protect crew in the most intense sustained radiation environment any humans would ever occupy. It would need thermal management systems capable of handling the heat flux at Mercury's distance from the Sun. It would need a propulsion system powerful enough to decelerate into Mercury orbit and later accelerate back toward Earth. And it would need the fuel for all of those maneuvers. The Apollo Command and Service module that carried 3 astronauts to the Moon and back had a mass of roughly 30 metric tons. The delta-V it needed for the entire round trip, from Earth orbit to lunar orbit and back, was roughly 4 to 5 kilometers per second. The crewed vehicle for a Mercury round trip would need a delta-V many times larger, potentially in the range of 20 to 30 kilometers per second or more, depending on the trajectory and mission profile. The rocket equation relates delta-V to the mass ratio of a vehicle, the ratio of its fully fueled mass to its empty mass. For chemical propulsion with a specific impulse in the range of 300 to 450 seconds, a delta V of 25 kilometers per second produces a mass ratio so extreme that for every kilogram of payload you want to deliver, you need hundreds or thousands of kilograms of propellant. The total vehicle mass for a crewed Mercury round trip using chemical propulsion would be measured not in hundreds of metric tons, but in tens of thousands, potentially more. For reference, the Saturn V rocket that launched Apollo missions to the Moon had a total liftoff mass of roughly 3,000 metric tons and could deliver about 45 metric tons to a trajectory toward the Moon. The mass required for a crewed Mercury round trip would demand a launch campaign of a scale that dwarfs anything in the history of spaceflight. Dozens of heavy-lift launches just to assemble the vehicle in orbit. Years of preparation before the mission even begins. A logistics chain of unprecedented complexity for a destination that nobody has ever landed on. And gravity assists, the technique that makes robotic missions possible, become largely impractical for crewed flights. Gravity assists work precisely because they are slow. Each flyby shaves off a portion of excess velocity, but the spacecraft must then travel to the next flyby opportunity, which may be months or years away. The multi-year timelines that make gravity assists effective for robots are the exact timelines that make them lethal for crews. Radiation exposure accumulates, bone density decreases, muscle atrophies, psychological strain compounds. The longer the mission, the more the crew deteriorates and the more consumables are needed. There is no version of a crewed Mercury mission that can afford to spend 7 or 8 years in transit. This creates a trap that has no clean engineering solution. A fast trajectory requires enormous fuel. A slow trajectory requires enormous life support. Both require enormous mass, and the delta V budget for Mercury, already brutal, applies to every kilogram of that mass equally. The rocket equation does not care whether the payload is instruments or people. It demands the same exponential fuel penalty regardless. There is another factor that makes Mercury uniquely punishing compared to other difficult destinations: aerobraking. When a spacecraft arrives at Mars, it can use the Martian atmosphere to slow down. The atmosphere is thin, but it is there. And by skimming through it at carefully calculated altitudes, a spacecraft can shed significant velocity without burning any fuel. This technique, called aerobraking or aerocapture, depending on the specific method, has been used successfully by multiple Mars missions. It dramatically reduces the fuel needed for orbit insertion and landing. Venus has an even thicker atmosphere, making aerobraking even more effective there in principle. Titan, Saturn's largest moon, has a dense atmosphere that the Huygens probe used to descend to the surface without retro-rockets. Mercury has no atmosphere, none. Its surface boundary exosphere is so thin that its pressure is less than 1/1,000,000th of Earth's. There is nothing to push against, nothing to slow you down. Every single meter per second of deceleration, from orbit insertion to final touchdown, must come from your engines. Every bit of slowing requires fuel. And every kilogram of that fuel had to be launched from Earth and carried across the entire multi-year journey. This is the first layer of the trap, and most people never even get past it. They assume Mercury is close, so it must be easy. They assume falling toward the Sun means you naturally end up near Mercury. They assume that small planets near bright stars are simple destinations. Every single one of those assumptions is wrong. Mercury sits at the bottom of the deepest gravity well in the solar system, moving faster than any other planet, offering no atmospheric assistance, protected by a gravitational sphere of influence so small that capture windows are measured in minutes. Reaching it requires either enormous fuel expenditure or years of patient gravity assist maneuvers that no crewed mission can afford. And here is what makes it worse. Everything described so far is just the outbound trip, just getting there. The return journey faces every single one of these problems again, but in reverse, and with a crew that has already been exposed to months or years of the most intense radiation environment any human has ever endured. Launching from Mercury's surface means climbing out of Mercury's gravity. Then it means climbing outward against the sun's pull, fighting uphill in the deepest part of the solar system's gravitational terrain. The delta V required to return from Mercury to Earth is not smaller than the delta V to arrive. In many trajectory analyses it is comparable, and depending on mission geometry, it can be larger. A round trip to Mercury is not twice as hard as a one-way trip. It is exponentially harder because every kilogram of return fuel must itself be carried to Mercury, which means it must be accounted for in the outbound fuel budget, which means the outbound fuel budget grows, which means more fuel is needed to carry that fuel, which means the total mass of the vehicle spirals upward through the rocket equation until the numbers become physically absurd. This is not an exaggeration. It is arithmetic, the same arithmetic that has kept every space agency on Earth from ever seriously proposing a crewed Mercury mission. When BepiColombo's Mercury surface element was cancelled in 2003 due to budget constraints, it was a small robotic lander, 44 kilograms, designed to survive roughly 1 week on the surface. It would have been delivered to Mercury on a one-way trip with no return capability. A week of operation for a package lighter than a large dog. That was the most ambitious surface mission anyone was willing to attempt. In 2020, the Applied Physics Laboratory proposed a Mercury lander concept for NASA's New Frontiers program. If selected, it would launch in 2035 and arrive in 2045, 10 years of transit for a robotic lander, one way. No return. That is the state of Mercury exploration. The most capable space agencies on the planet, with decades of experience sending robots across the solar system, treat Mercury as an extreme destination. They spend billions of dollars and nearly a decade of flight time to place a single orbiter around it. They cancel lander missions because even a 44-kilogram one-way surface package is too expensive and too complex. They have never, not once, flown a mission to Mercury that was designed to come back. And yet people casually refer to Mercury as a small planet close to the Sun, as if closeness means accessibility, as if size means simplicity. Mercury is neither accessible nor simple. It is a destination that punishes every assumption, penalizes every kilogram, and offers no free deceleration, no atmospheric cushion, no margin for error. Getting there is already one of the hardest things a spacecraft can do. What happens after arrival is worse, because the orbital mechanics are only the first layer of the trap. Once you reach Mercury, once you slow down enough to enter orbit or descend to the surface, you enter an environment that attacks every system, every material, and every biological process that a human mission depends on. The Sun is no longer a distant star providing comfortable warmth. At Mercury's distance, it is a furnace. It fills a portion of the sky more than twice as wide as it appears from Earth, and it delivers energy at an intensity that turns spacecraft engineering into a thermal survival problem with no permanent solution. The environment is waiting, and it does not forgive. There is a moment in every Mercury mission where the spacecraft crosses an invisible threshold. No alarm sounds, no boundary line appears on the navigation display. But the engineers on the ground know it has happened because the thermal readings start climbing and they do not stop. The Sun, which from Earth appears as a modest disk, roughly half a degree across, begins to grow. At Mercury's average orbital distance of approximately 58 million kilometers, the Sun appears more than 2.5 times wider than it does from Earth. At perihelion, when Mercury swings to within 46 million kilometers of the Sun, that disk swells to more than 3 times its apparent size from our planet. The difference is not just visual, it is energetic. The intensity of solar radiation follows an inverse square law. Cut the distance to the Sun in half, and the radiation intensity quadruples. At Mercury's average distance, the solar flux is roughly 6 to 7 times what Earth receives. At perihelion, it peaks at approximately 11 times Earth's level. That energy has nowhere to go. There is no atmosphere to scatter it, no clouds to reflect it, no ocean to absorb and redistribute it. It hits the surface directly, and the surface responds with temperatures that make Mercury one of the most thermally extreme solid bodies in the entire solar system. But Mercury's thermal story is not a simple tale of relentless heat. It is far stranger than that, and far more dangerous. To understand why, you need to understand how Mercury rotates. Most planets rotate in a way that gives them a recognizable day-night cycle. Earth spins once every 24 hours. Mars takes about 24 hours and 37 minutes. Even Venus, which rotates backwards and extraordinarily slowly, has a clear rotational period. Mercury does something different. It is locked in what scientists call a 3-to-2 spin-orbit resonance with the Sun. For every 2 complete orbits Mercury makes around the Sun, it rotates exactly 3 times on its axis. This is not tidal locking in the way the Moon is locked to Earth, where the same face always points toward the parent body. Mercury does rotate, but its rotation and its orbit are coupled in a precise mathematical ratio that produces one of the most alien day-night cycles in the solar system. The result is this: 1 solar day on Mercury, measured from sunrise to sunrise at a given point on the surface, lasts approximately 176 Earth days. That is 2 full Mercury years. The planet completes an entire orbit around the Sun, comes all the way back to roughly the same position, and completes another full orbit before the Sun returns to the same position in a local observer's sky. This means that any point on Mercury's equator experiences roughly 88 Earth days of continuous sunlight, followed by roughly 88 Earth days of continuous darkness. 88 days of relentless solar bombardment at 6 to 11 times Earth's intensity, followed by 88 days of exposure to the vacuum of space, with no atmospheric blanket to retain any heat. The temperatures that result from this cycle are extraordinary. On the day side, surface temperatures at the equator reach approximately 420 degrees Celsius. That is hot enough to melt zinc, hot enough to melt tin, hot enough to melt lead, which liquefies at 327 degrees Celsius. The surface rock glows with thermal energy, radiating infrared radiation back into space and outward toward anything in orbit above it. Messenger's orbit was designed specifically to minimize the time the spacecraft spent over the sunlit surface, because the combination of direct solar radiation from above and thermal radiation from the scorching ground below created a heating environment that exceeded what the spacecraft's thermal control systems could sustain for long periods. On the night side, the temperature plunges to approximately negative 170 degrees Celsius. Some estimates place the coldest nightside temperatures even lower, approaching negative 180 degrees Celsius in certain regions. That is colder than the surface of most objects in the outer solar system, colder than the night side of the Moon, colder than anywhere on Mars at any time of year. The reason for such extreme cold is the same reason the day side gets so hot. There is no atmosphere, no insulating blanket of gas to trap heat after sunset. The moment a point on the surface rotates out of direct sunlight, it begins radiating its thermal energy into the vacuum of space, and there is nothing to slow that process down. The ground cools rapidly, and over the course of 88 days of darkness, it reaches temperatures that would freeze carbon dioxide solid. The temperature swing between day and night at Mercury's equator is therefore roughly 590 degrees Celsius. Nearly 600 degrees of thermal range experienced over and over every single Mercurian solar day. No other solid body in the solar system exhibits a thermal swing this severe. The Moon, which also lacks a significant atmosphere, sees temperature ranges of roughly 300 degrees Celsius. Mars, with its thin atmosphere, experiences swings of perhaps 70 to 100 degrees Celsius, depending on latitude and season. Mercury's thermal range is in a category entirely by itself. But even that figure, as extreme as it is, hides a deeper layer of thermal complexity. Because the 600-degree swing is an average. Some parts of Mercury's equator get significantly hotter than others, and the reason involves an interaction between Mercury's rotation and its orbit that produces a thermal phenomenon found nowhere else in the solar system. Mercury's orbit is not circular. It is one of the most eccentric orbits of any planet, with a distance from the Sun that varies between roughly 46 million kilometers at perihelion and roughly 70 million kilometers at aphelion. That is a difference of nearly 24 million kilometers, more than 50% of the minimum distance. The solar flux at perihelion is therefore more than twice the flux at aphelion. When Mercury is closest to the Sun, the energy hammering its surface is dramatically more intense than when it is farthest away. Now combine that orbital eccentricity with the 3:2 spin-orbit resonance. Because the rotation and orbit are locked in a precise ratio, the same two longitudes on Mercury's equator always face the Sun directly at perihelion. These are separated by 180 degrees, sitting on opposite sides of the planet. Every time Mercury reaches its closest approach to the Sun, one of these two longitudes is pointed straight at the solar disk at the moment when the Sun is at its nearest, largest, and most intense. The other faces it one orbit later when the geometry repeats. These two equatorial zones receive substantially more cumulative solar energy per orbit than any other region of the planet. Scientists refer to them as the hot poles or hot longitudes. They are not poles in the geographic sense. They are thermal poles, the points on the surface that absorb the most concentrated solar punishment over time. Peak surface temperatures at these hot longitudes can exceed 430 degrees Celsius, pushing beyond the equatorial average and into a range where the surface conditions are even more severe than the already brutal figures normally quoted for Mercury. The longitudes, 90 degrees away from the hot poles, present the opposite case. These regions face the Sun most directly at aphelion, when Mercury is at its greatest distance and the solar flux is at its weakest. They still experience extreme temperatures by any earthly standard, but their peak dayside readings are measurably lower than the hot poles. The temperature difference between the hottest and coolest equatorial longitudes is not trivial. It is significant enough to produce different thermal weathering patterns across the surface, different rates of volatile loss from the regolith, and different thermal stress profiles for any equipment placed at different longitudes. For a human mission, this has a direct and uncomfortable consequence. The thermal environment on Mercury is not uniform even among equatorial landing sites. A mission planner cannot simply ask how hot Mercury gets at the equator and design for that single number. They must ask which longitude the landing site occupies, what the orbital phase will be during surface operations, and how the thermal peak at that specific longitude compares to the thermal peak at other candidate sites. A habitat placed at a hot longitude site faces peak temperatures tens of degrees higher than an identical habitat placed 90 degrees away. Those extra tens of degrees may sound small against a 600-degree total swing, but at the margins of materials performance, where thermal expansion coefficients seal integrity, and radiator efficiency are already being pushed to their theoretical limits, every additional degree matters. It is one more variable in a design problem that already has too many. The hot longitude phenomenon also means that Mercury's thermal assault is not just about the day-night cycle. It is about which day and where. The same location on the surface experiences a different peak temperature depending on where Mercury is in its orbit when local noon occurs. A crew that arrives during a period when their site is in its hot longitude phase faces a more severe thermal environment than a crew arriving at the same site half a Mercury year later. Mission timing and surface longitude are coupled through orbital mechanics in a way that no other planetary destination requires. Mars does not have this problem. The Moon does not have this problem. Only Mercury, with its unique combination of high eccentricity and spin-orbit resonance, produces a thermal geography that shifts with orbital phase and creates permanent zones of enhanced heating locked to specific longitudes. This is the kind of detail that vanishes from popular descriptions of Mercury but dominates the engineering reality. It is another example of how Mercury's individual hazards interact with each other to create compounding difficulties. The thermal swing alone is extreme. The orbital eccentricity alone is notable. The spin-orbit resonance alone is unusual. But the three of them together produce a thermal environment that is not just hot, not just variable, but geographically and temporally structured in ways that add design constraints no other destination imposes. Every layer of Mercury's environment, when examined closely, reveals another layer underneath. For a human mission, this thermal environment creates a problem that has no straightforward engineering solution. Every material expands when heated and contracts when cooled. A 600-degree thermal cycle means that any structure on Mercury's surface, any habitat, any vehicle, any piece of equipment, would be subjected to repeated thermal stress that would fatigue metals, crack ceramics, degrade seals, and warp structural components over time. On Earth, bridges and buildings are designed with expansion joints to handle temperature variations of perhaps 50 or 60 degrees Celsius. Mercury demands materials and designs that can handle 10 times that range. And the cycling is relentless. It does not stop. Every 176 Earth days, the entire temperature range repeats. Equipment that survives one cycle must survive the next, and the next, and the one after that. Fatigue failure is not a question of if, it is a question of when. The obvious response is to avoid the surface. Stay in orbit, operate from above. But orbit around Mercury comes with its own version of the same problem. A spacecraft in low Mercury orbit passes over the sunlit surface repeatedly, absorbing reflected visible light and thermal infrared radiation from the ground, while also receiving direct solar radiation on its sunward side. On the opposite side, facing deep space, temperatures drop toward the cosmic background. The spacecraft becomes a thermal battleground, with one face being roasted and the other face freezing, and the boundary between the two shifting constantly as the spacecraft orbits. Messenger managed this by using a sunshade, a ceramic cloth barrier that blocked direct sunlight, while the spacecraft's radiators dumped heat from the shaded side. BepiColombo uses a similar approach. But these are small, light, robotic probes with no crew, no life support systems, and no requirement to maintain a shirt-sleeve environment inside. A crewed vehicle would need vastly more internal volume, vastly more power for thermal regulation, and vastly more mass devoted to heat management. And every kilogram of thermal protection hardware is a kilogram that had to be launched from Earth and decelerated into Mercury orbit at enormous fuel cost. The thermal environment is relentless, but it is only part of the assault that Mercury's proximity to the Sun imposes. The radiation environment is equally punishing, and in some ways more dangerous because its effects are cumulative and invisible. At Earth's distance from the Sun, the solar wind, a continuous outflow of charged particles streaming from the Sun's corona, arrives with a certain density and energy. Earth's magnetic field, generated by the churning liquid iron in its outer core, extends tens of thousands of kilometers into space, creating a magnetosphere that deflects the vast majority of these particles away from the surface. The magnetosphere acts as an invisible shield. Without it, the solar wind would strip away the atmosphere and bombard the surface with ionizing radiation. Earth's magnetic field is strong enough that the magnetosphere's boundary on the sunward side, called the magnetopause, typically sits at a distance of roughly 10 Earth radii from the planet's center. The shielded region is enormous. Mercury has a magnetic field. This was one of the surprises from Mariner 10's flybys in the 1970s. A planet that small, with a rotation period that slow, was not expected to generate a global magnetic field. And yet, it does. Mercury's magnetic field is dipolar, roughly aligned with its spin axis, and unmistakably real. But it is weak, approximately 1% the strength of Earth's magnetic field. The magnetopause on Mercury's sunward side sits only about 1 to 1.5 Mercury radii from the planet's center. The protected region is small, desperately small, and the solar wind at Mercury's distance is far denser and more energetic than at Earth. The combination of a weak field and an intense wind means that Mercury's magnetosphere is compressed, dynamic, and prone to events that would never occur at Earth. One of the most alarming findings from MESSENGER's mission was that the solar wind can, under certain conditions, compress Mercury's magnetosphere so severely that the magnetopause retreats below the surface of the planet. When this happens, the solar wind directly impacts the surface. Charged particles, primarily protons and electrons, slam into the regolith at high velocities, sputtering atoms from the surface and contributing to Mercury's tenuous exosphere. For a human on or near Mercury, this is not an academic detail. It means that during periods of high solar activity, there is no magnetic protection at all. The surface is exposed to the full force of the solar wind, and any crew on the surface or in low orbit would receive a radiation dose with no natural shielding between them and the Sun. MESSENGER also discovered that Mercury's magnetic field is not centered symmetrically on the surf planet. It is offset significantly northward by roughly 480 kilometers from the geometric center. This means the magnetic field is stronger in the northern hemisphere and weaker in the south. The practical consequence is that the southern hemisphere's surface is substantially less protected from solar wind bombardment than the north. Charged particles that the field deflects away from northern latitudes penetrate much closer to the ground in the south. Any surface location in Mercury's southern hemisphere sits under a thinner magnetic umbrella than an equivalent site in the north, and even the northern umbrella is barely adequate by any human-rated standard. This asymmetry was confirmed across years of MESSENGER orbital data and is expected to be studied in greater detail by BepiColombo. For mission planning, it means that the radiation environment on Mercury is not just severe, it is geographically uneven in ways that add another variable to an already over-constrained design problem. Every candidate landing site or orbital profile must account for the lopsided field, and the best protected locations still fall far short of what a human crew would require. BepiColombo's flybys have already begun to complicate the magnetospheric picture further. During the third Mercury flyby in June of 2023, instruments aboard the MEO magnetospheric orbiter detected a layer of turbulent plasma at low latitudes along the magnetosphere's edge. This boundary layer contained particles with energies reaching up to 40 kilo-electron-volts, a range far broader than anything previously measured in Mercury's magnetic environment. Researchers also found energetic hot hydrogen ions trapped near Mercury's equatorial plane with energies around 20 kilo-electron-volts. These are not theoretical predictions. They are measurements, taken in situ, of a radiation environment that turned out to be more energetic and more complex than the models predicted. Every new observation of Mercury's magnetosphere has revealed additional components of the radiation hazard. The models built from messenger data are being revised upward. The actual environment is worse than what the textbooks describe, and for any crewed mission, worse than expected is a phrase that translates directly into more shielding mass, which translates into more fuel, which translates into a mission architecture that was already impossible, becoming even more so. The solar wind is not the only radiation concern. Solar energetic particle events, sometimes called solar proton events, occur when the sun releases bursts of high-energy protons during solar flares or coronal mass ejections. These events are unpredictable, can last hours to days, and the energies involved are high enough to penetrate spacecraft hulls and habitat walls. At Earth's distance, a major solar energetic particle event can deliver a radiation dose that exceeds safe limits for astronauts on the International Space Station, which orbits within Earth's magnetosphere. At Mercury's distance, the particle flux from such an event would be 6 to 10 times more intense. The inverse square law applies to particle radiation just as it does to light. A solar proton event that is dangerous at Earth becomes potentially lethal at Mercury. To understand what this means in concrete terms, consider one of the most powerful solar energetic particle events in recent history. In August of 1972, between the Apollo 16 and Apollo 17 missions, the Sun unleashed a massive proton event. Had astronauts been on the lunar surface during that event, outside the protection of Earth's magnetosphere, radiation models suggest they would have received a dose sufficient to cause acute radiation sickness. Some analyses indicate the dose could have been lethal within hours without adequate shielding. That event occurred at Earth's orbital distance of roughly 150 million kilometers from the Sun. At Mercury's distance of 46 to 70 million kilometers, the same event would have delivered a proton flux between 4 and 10 times more intense. The dose rate would not merely cause sickness. It would overwhelm any shielding system of reasonable mass and deliver a radiation exposure measured in grays rather than milligrays. The difference between those two units is the difference between long-term cancer risk and immediate tissue destruction. And the event of 1972, while severe, was not even the most powerful solar proton event recorded in the modern era. The Carrington event of 1859, inferred from ice core and geomagnetic records, was likely far more intense. Events of that magnitude are estimated to occur roughly once per century. A crewed Mercury mission lasting months to years would face a non-zero probability of encountering such an event, with no planetary magnetic field for protection and no possibility of rapid evacuation. This creates a mission planning problem that borders on unsolvable. Solar energetic particle events cannot be reliably predicted more than a few hours in advance. A crew at Mercury would need a radiation shelter capable of reducing the particle dose to survivable levels, and they would need to reach it quickly when an event is detected. On the International Space Station, astronauts shelter in the most heavily shielded sections of the station during such events. But the ISS is inside Earth's magnetosphere, which already provides significant protection. At Mercury, the shelter must do all the work. The shielding mass required to reduce a major solar proton event to safe levels is substantial. Water, polyethylene, and other hydrogen-rich materials are effective radiation shields, but they are heavy. Every kilogram of shielding is another kilogram that must be carried from Earth, accelerated, decelerated, and managed across the entire mission architecture. And the shielding must be effective against both solar energetic particles and the continuous background of galactic cosmic rays, which are high-energy particles from outside the solar system that penetrate even thick shielding. Galactic cosmic rays deserve their own mention because they represent a qualitatively different threat from solar radiation. These particles, primarily protons and heavier atomic nuclei, accelerated to near light speed by supernova remnants and other extreme astrophysical sources, carry enormous energy. A single heavy galactic cosmic ray nucleus can damage DNA, kill cells, and initiate cascading secondary particle showers when it strikes shielding material. The secondary particles can be as damaging as the primary. Thick shielding actually increases the secondary particle dose in some configurations, creating a counterintuitive problem where more material does not always mean less radiation exposure. At Earth's surface, the atmosphere provides roughly the equivalent of 10 meters of water in shielding against cosmic rays. At Mercury, there is no atmosphere and a negligible magnetic field. The full flux of galactic cosmic rays reaches the surface and any spacecraft in orbit without attenuation. For a crewed mission lasting months or years in Mercury's environment, the cumulative radiation dose from the combination of enhanced solar wind, periodic solar energetic particle events, and unshielded galactic cosmic rays would exceed every guideline established by every space agency for acceptable astronaut exposure. The risk of radiation-induced cancer, central nervous system damage, cataracts, and cardiovascular disease would be profound. Mitigating this risk to acceptable levels would require either extremely heavy shielding, which the mission architecture cannot afford to carry, or extremely short mission durations, which the orbital mechanics and fuel budgets do not allow. The radiation and the thermal extremes do not exist in isolation. They interact. High temperatures degrade the performance of electronic systems, which are simultaneously being damaged by radiation. Thermal cycling induces mechanical stresses in the same components that ionizing radiation is making brittle. The combination accelerates failure rates beyond what either factor would produce alone. Messenger experienced progressive degradation of several systems during its 4 years in Mercury orbit, and it was a robotic probe with no biological components to protect. The thermal and radiation environments are not separate challenges to be solved independently. They are synergistic stressors that compound each other's effects on both hardware and humans. There is one feature of Mercury that might initially appear to offer hope: water, ice. In the 1990s, Earth-based radar observations detected highly reflective patches at Mercury's poles. Messenger subsequently confirmed that these patches are deposits of water ice sitting in permanently shadowed craters near the north and south poles. The geometry works because Mercury's rotational axis is nearly perpendicular to its orbital plane, with a tilt of only about 2 arc-minutes, essentially 0. This means the sun never rises more than a few degrees above the horizon at the poles, and the floors of deep craters at high latitudes never receive direct sunlight. These permanently shadowed regions reach temperatures as low as approximately -170 degrees Celsius or colder, which is sufficient to keep water ice stable over billions of years. The ice is real. Messenger mapped it. The deposits are significant. Some are covered by a thin layer of dark organic material that insulates the ice from any slight thermal input. The presence of water ice on the closest planet to the Sun is one of the great scientific discoveries of Mercury exploration, and it has led to speculation that a human outpost could potentially use polar ice as a resource. Water can be split into hydrogen and oxygen, providing breathable air and rocket propellant. In theory, polar ice deposits could enable a self-sustaining presence. In practice, the ice does not solve the problem. It barely dents it. The permanently shadowed craters where ice exists are among the most thermally and operationally challenging locations on Mercury. They sit in permanent darkness, which means no solar power. Temperatures in the shadows hover near -170 degrees Celsius, which creates a cryogenic operating environment that requires its own suite of engineering solutions. And the craters are surrounded by terrain that is in direct sunlight, where temperatures soar to hundreds of degrees Celsius. Moving between an ice-bearing shadowed crater and any sunlit area means crossing a thermal gradient of 500 degrees or more over a distance of meters to kilometers. Equipment and crew would need to function across this gradient or be designed exclusively for one thermal regime, severely limiting operational flexibility. Extracting and processing the ice would require mining equipment, processing facilities, storage systems, and power generation, none of which can operate easily at -170 degrees Celsius in permanent shadow with no solar energy input. Nuclear power is the obvious alternative, but a nuclear reactor adds mass, complexity, and its own shielding requirements to a mission that is already crushed under the weight of every other engineering demand. And even if you extract the ice, even if you split it into hydrogen and oxygen, the quantities needed for a crewed return mission are enormous. Rocket propellant is measured in tens of thousands of kilograms for interplanetary trajectory changes. Mining, processing, and storing that quantity of propellant from polar ice deposits on a planet with no infrastructure, no atmosphere, and a surface that oscillates between blast furnace heat and deep space cold is not a solution. It is a second mission grafted onto the first, each one individually at the far edge of what is technically conceivable. During BepiColombo's sixth and final flyby in January of 2025, the monitoring cameras imaged several of the permanently shadowed polar craters where Messenger had detected ice. The craters Prokofiev, Kandinsky, Tolkien, and Gordimer were photographed from a new geometry, providing views that complemented Messenger's earlier radar and neutron data. These images are among the first direct visual observations of the regions where Mercury's water ice is believed to exist. They reveal terrain that is geologically complex, with crater walls and floors shaped by billions of years of impact history and thermal fracturing. The images confirm what the data already suggested. These are not smooth, accessible ice fields. They are rough, deeply shadowed depressions in some of the most extreme terrain on the planet. Accessing them would require navigating steep crater walls in permanent darkness at cryogenic temperatures, surrounded by sunlit terrain, hundreds of degrees hotter just beyond the shadow's edge. The ice is there. Getting to it is another engineering problem stacked on top of every other engineering problem Mercury imposes. There is one more environmental factor that rarely gets discussed, but profoundly affects the viability of any surface. Operations on Mercury. The regolith. Mercury's surface is covered in a layer of broken rock and dust, produced by billions of years of meteorite bombardment. Unlike the Moon, which has at least a minimal magnetic field and sits much farther from the Sun, Mercury's regolith is continuously processed by solar wind sputtering, micrometeorite impacts, and intense ultraviolet radiation. The result is a surface material that is electrostatically charged, chemically reactive, and potentially abrasive in ways that lunar regolith, which already caused significant problems during the Apollo missions, cannot match. During the Apollo program, lunar dust clung to spacesuits, clogged joints, abraded visors, and infiltrated seals despite every precaution. Astronauts reported that the dust smelled like spent gunpowder and irritated their lungs during brief exposures inside the lunar module. Lunar surface stays lasted days at most. A Mercury surface mission would need to contend with a similar or worse dust problem over far longer time periods in a thermal and radiation environment that makes every mitigation strategy harder to implement. Seals that work at room temperature may fail at 400 degrees Celsius. Filters designed for one atmospheric composition may not handle the chemically altered regolith particles of Mercury's surface. And every mechanical failure, every seal breach, every clogged vent is a potential mission-ending event when there is no resupply, no rescue, and no atmosphere to breathe if the habitat is compromised. Mercury's environment does not present a single dramatic threat. It does not have a crushing atmosphere like Venus. It does not have the immediate lethality of a gas giant's radiation belts. It does not kill instantly in any one obvious way. What it does is worse for mission planning. It presents a matrix of simultaneous, interacting, compounding threats: extreme heat, extreme cold, extreme thermal cycling, intense solar radiation, periodic lethal particle events. A negligible magnetic field, no atmosphere, no aerobraking, electrostatically charged regolith, a day-night cycle measured in months, and cryogenic polar regions that offer tantalizing resources behind walls of engineering difficulty so high that accessing them may cost more than they provide. Each of these factors, taken individually, is a serious engineering challenge. Some of them have been addressed for robotic missions through clever design and the acceptance of limited mission lifetimes. Messenger lasted 4 years. BepiColombo is designed for 1 year of primary science operations with a possible 1-year extension. These are short timescales, acceptable for robots that do not need food, water, oxygen, or radiation protection to the standards required for humans. For a crewed mission, every one of these factors must be solved simultaneously, for a duration measured in months at minimum, with reliability margins that protect human life. No system can be allowed to fail in a way that is not immediately recoverable. No thermal event can be allowed to breach the habitat. No radiation event can be allowed to exceed the shielding capacity. No mechanical system can be allowed to degrade past the point of safe operation. And all of this must be maintained on a world that cycles through the most extreme thermal environment of any solid planet, bathed in the most intense radiation of any planetary surface. With no atmosphere and a magnetic field that sometimes collapses entirely under solar pressure, the environment does not forgive. It does not pause. It does not offer a safe harbor. It simply continues, day after relentless day, 176 Earth days at a time, oscillating between furnace and freezer, between scorching light and absolute dark. While the sun pours energy onto the surface at an intensity that no human has ever endured and no crewed spacecraft has ever been designed to withstand for extended periods. And yet, remarkably, the environment is still not the deepest part of the trap. A crew could conceivably be sheltered, at enormous cost and complexity, from the heat, the cold, the radiation, and the dust. The engineering is at the outer boundary of imagination, but it is not physically impossible in principle. What pushes Mercury from extraordinarily difficult to effectively impossible is what comes next. The part of the mission that nobody has a credible plan for. The part that turns Mercury from a hostile destination into a one-way commitment. Because surviving on Mercury, as hard as that would be, is only the second problem. The first problem was getting there. And the third problem, the one that closes the trap, is getting back. That problem involves every difficulty described so far, compounded by the fact that you are now starting from the worst possible location in the solar system to begin a journey home, deep in the sun's gravity well. On a world with no atmosphere to help you launch, carrying a crew that has already been damaged by months of radiation exposure. With a fuel budget that was punishing on the outbound trip and becomes functionally impossible for the return, the trap is not one thing, it is everything, layered together, reinforcing itself at every stage. And the return is where the layers, finally, become walls. There is a phrase that mission planners use when discussing destinations where the return trip is harder than the outbound journey. They call it an asymmetric mission. Mars is mildly asymmetric. The Moon is nearly symmetric. Mercury is so deeply asymmetric that the word barely applies. The return from Mercury is not just harder than getting there. It is a fundamentally different class of problem, one that takes every difficulty of the outbound trip and amplifies it through the most unforgiving arithmetic in spaceflight. To understand why, start with where you are. You have arrived at Mercury. You are either in orbit or on the surface. Behind you is a journey that consumed years of flight time, multiple gravity assists, and an amount of energy comparable to reaching the outer solar system. Ahead of you is the return. And the return begins from the worst starting position any crewed mission could occupy. Mercury sits deep inside the sun's gravity well. That well is not a metaphor. It is a measurable quantity. Gravitational potential energy decreases as you move closer to the sun. Climbing out of that well, moving from Mercury's orbital distance back to Earth's, requires adding an enormous amount of kinetic energy to your spacecraft. You must accelerate outward, away from the sun, against the sun's gravitational pull. Every meter per second of velocity you gain is a meter per second the sun's gravity is working to take back. And the starting deficit is massive. Recall that Mercury orbits the sun at an average velocity of roughly 47 kilometers per second, peaking near 59 kilometers per second at perihelion. Earth orbits at roughly 30 kilometers per second. To transfer from Mercury's orbit to Earth's orbit, a spacecraft must increase its heliocentric velocity substantially. The exact delta V depends on the specific transfer trajectory and the relative positions of the two planets at the time of departure. But a basic Hohmann transfer from Mercury's orbit to Earth's orbit requires a velocity change on the order of several kilometers per second just to enter the transfer ellipse, followed by another significant velocity change at Earth to match orbits or enter the Earth system. These are large numbers. They are on the same order as the delta V required for the outbound trip. In some geometries, the return delta V is slightly larger. Now, add the delta V required to leave Mercury itself. If you are on the surface, you must first launch to orbit. Mercury's surface gravity is roughly 3.7 meters per second squared, about 38% of Earth's. That sounds manageable compared to launching from Earth, but remember that Earth has an atmosphere and Mercury does not. When a rocket launches from Earth, it can be designed for sea-level atmospheric pressure. Engineers understand the environment completely. On Mercury, the launch happens in a vacuum from a surface that may be at 400 degrees Celsius or negative 170 degrees Celsius, depending on the time of the Mercurian day. The thermal state of the launch vehicle, the propellant, the engine nozzles, and every structural component is dictated by whichever extreme the local environment imposes at the time of departure. Propellant management in these conditions is its own engineering nightmare. Cryogenic fuels boil off in the heat. Hypergolic fuels may behave unpredictably at temperature extremes. Every system must be designed for thermal conditions that no launch vehicle in history has ever been required to handle. Reaching low Mercury orbit from the surface requires a delta V of roughly 3 to 4 kilometers per second, depending on the orbit altitude and the efficiency of the ascent trajectory. That is less than Earth's orbital velocity requirement of roughly 7.7 kilometers per second, but it is not trivial. And it must be achieved with propellant that has been stored on Mercury's surface through whatever thermal cycling the mission endured. Propellant that was brought from Earth, carried across the entire outbound journey, landed on Mercury, kept in usable condition during surface operations, and is now expected to perform flawlessly in an environment that alternates between roasting and freezing every 88 days. Once in Mercury orbit, the spacecraft must then perform the trans-Earth injection burn, the engine firing that raises its orbit away from Mercury and places it on a trajectory back toward Earth. This burn must overcome Mercury's gravitational influence and add enough velocity to climb outward through the Sun's gravity well to intersect Earth's orbit at the right time and position. The delta V for this maneuver is substantial. Combined with the surface-to-orbit delta V and the mid-course corrections and Earth orbit insertion burns that will be needed later, the total return delta V budget is enormous. Here is where the rocket equation becomes truly cruel. Every kilogram of propellant needed for the return journey must be present at Mercury at the time of departure. That propellant had to be carried from Earth. It had to be accelerated out of Earth's gravity well, decelerated across the inner solar system, and delivered to Mercury's orbit or surface intact and usable. The mass of return propellant is therefore part of the outbound payload, and the outbound journey has its own massive propellant requirement. The propellant needed to carry the return propellant to Mercury adds to the total outbound mass, which increases the outbound propellant requirement, which increases the total launch mass, which requires more propellant to lift from Earth, which increases the total mass further. This is the tyranny of the rocket equation, expressed in its most vicious form. The relationship between payload mass and propellant mass is exponential, not linear. Doubling the payload does not double the fuel. It more than doubles it. And for a destination like Mercury, where both the outbound and return delta V budgets are among the highest in the solar system, the exponential penalty stacks on itself twice. To make this concrete, consider a simplified comparison with Mars, the destination that dominates human spaceflight planning. A crewed Mars mission is already at the far edge of current engineering capability. Decades of study by NASA, ESA, and private organizations have produced mission architectures that require enormous spacecraft, years of transit, and launch vehicles that do not yet exist. The total delta V for a round trip to Mars, including Earth departure, Mars orbit insertion, landing, surface-to-orbit launch, Mars departure, and Earth return, is in the range of roughly 12 to 16 kilometers per second, depending on the trajectory and whether aerobraking is used. Mars missions rely heavily on aerobraking. The Martian atmosphere, though only about 1% the density of Earth's at the surface, is thick enough to provide meaningful deceleration. Every Mars lander, from Viking to Curiosity to Perseverance, has used atmospheric entry to shed the majority of its arrival velocity. Parachutes deploy, heat shields absorb kinetic energy. By the time retro rockets fire for final descent, most of the deceleration has already been accomplished for free, courtesy of the atmosphere. This saves thousands of kilograms of propellant. It is not an optimization, it is an enabling technology. Without Martian aerobraking, the fuel budget for landing on Mars would be so large that most proposed mission architectures would collapse under their own mass. Mercury offers none of this. Zero atmospheric deceleration. Every meter per second from orbit to surface must come from engines burning propellant, and the thermal environment during descent adds its own penalty. A spacecraft descending toward Mercury's sunlit surface is flying into an intensifying field of infrared radiation from the ground, while simultaneously absorbing direct solar radiation. Thermal management during powered descent is an engineering problem that has never been solved for any spacecraft at Mercury, robotic or otherwise. No spacecraft has ever performed a controlled landing on Mercury. Not Messenger, which never attempted one. Not BepiColombo, which will orbit but never touch the surface. The technology to land softly on Mercury and survive has never been built, never been tested, and never been funded past the concept stage. The 44-kilogram surface element that was cancelled from BepiColombo would have been the first attempt, using airbags and a semi-hard impact after a propulsive braking phase. It was designed to survive the landing with roughly a 30-meter-per-second impact velocity. That is not a gentle touchdown. It is a controlled crash, deemed acceptable for a small robotic package. A crewed vehicle requires a controlled, soft landing, which demands far more propellant and far more precise guidance. The comparison with Mars extends further. Mars has resources that can be exploited to reduce the return propellant burden. The Martian atmosphere is 95% carbon dioxide. Multiple mission architectures, most notably those proposed by Robert Zubrin in the Mars Direct concept, rely on in-situ resource utilization to manufacture return propellant on Mars using atmospheric carbon dioxide and a small amount of imported hydrogen. The Sabatier reaction and related processes can produce methane and oxygen from Martian atmospheric inputs, potentially eliminating the need to carry return propellant from Earth. This is a transformative concept. If it works, it breaks the exponential tyranny of the rocket equation by producing the return fuel at the destination rather than carrying it from the origin. NASA's Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, which flew on the Perseverance rover, demonstrated the production of oxygen from Martian carbon dioxide on the surface of Mars. The technology is real. The chemistry works. The engineering is being developed. Mercury has no equivalent. There is no atmosphere to process. The polar water ice deposits, while scientifically fascinating, are not a practical propellant source for the reasons discussed earlier. They exist in permanently shadowed craters at cryogenic temperatures in locations with no solar power access. Mining the ice would require establishing a complete industrial operation in one of the most hostile surface environments in the solar system. Transporting the extracted water or its electrolysis products from the polar regions to any launch site would mean crossing thermal gradients of hundreds of degrees. And the total quantity of ice, while significant in scientific terms, is unknown in terms of accessible volume. Messenger detected the ice through radar and neutron spectrometer measurements, but the exact depth, purity, and spatial distribution of the deposits remain uncertain. Planning a crewed return mission that depends on extracting thousands of kilograms of propellant from these deposits would mean betting crew survival on a resource whose characteristics are still being mapped by orbital instruments. Mars also has lower gravity than Mercury at the surface, 3.7, 2 meters per second squared, compared to Mercury's 3.7. The values are nearly identical, but Mars has something Mercury lacks entirely: a practical launch environment. Launching from Mars means launching through a thin atmosphere that provides negligible drag. Launching from Mercury means launching in a vacuum, which eliminates drag but also eliminates any possibility of aerodynamic lift or control during ascent. The launch vehicle must rely entirely on thrust vectoring and reaction control, and it must do so while managing thermal loads from either the sun-blasted or deep frozen surface beneath it. The ascent trajectory from Mercury must also account for the Sun's gravitational influence, which at Mercury's orbital distance is far stronger than at Mars. A vehicle launching from Mercury enters a gravitational environment where the Sun is the dominant force almost immediately upon leaving the surface, and every trajectory error is amplified by the Sun's pull. The timeline problem compounds everything. A crewed Mars mission using a Hohmann-like transfer orbit has a transit time of roughly 6 to 9 months in each direction. This is long but manageable with current life support technology and acceptable radiation exposure levels, especially if the transit vehicle includes a radiation shelter for solar energetic particle events. The total mission duration for a conjunction-class Mars mission, the most fuel-efficient type, is roughly 2 to 3 years, including surface stay time. A crewed Mercury mission faces a dilemma with no good solution. A fast trajectory minimizes crew exposure to the space radiation environment and reduces consumables requirements, but it demands an enormous delta-V that makes the fuel mass prohibitive. A slow trajectory using gravity reduces the fuel requirement, but extends the mission duration to years or even a decade, which is incompatible with crew survival. The Messenger mission took 7 years. BepiColombo is taking 8. These timelines work for robots. They do not work for humans who need food, water, oxygen, radiation protection, psychological support, and medical capability every single day. There is no efficient transfer orbit between Earth and Mercury that provides a short transit time and a low delta-V. The geometry of the inner solar system makes this impossible. A Hohmann transfer from Earth to Mercury takes roughly 105 days in each direction under idealized conditions. That sounds reasonable until you calculate the delta-V required. The velocity changes for a direct Hohmann transfer to Mercury orbit and back are so large that the propellant mass fraction, the ratio of fuel mass to total vehicle mass, exceeds what any known chemical propulsion system can achieve with a crewed payload. The spacecraft would be almost entirely fuel with an impossibly thin margin for structure, crew systems, and payload. Advanced propulsion technologies offer some theoretical relief, but none that fundamentally changes the picture. Nuclear thermal propulsion, which heats a propellant like hydrogen using a nuclear reactor, provides a higher specific impulse than chemical rockets, meaning more thrust per unit of propellant. This reduces the fuel mass fraction for a given delta-V, but the improvement, while significant for Mars missions, is not sufficient to make a crewed Mercury round trip feasible. The delta-V budget is simply too large. Even with nuclear thermal propulsion, the mass ratio remains punishing. Nuclear electric propulsion, which uses a reactor to power ion thrusters, offers even higher specific impulse, but at extremely low thrust levels. Ion engines are efficient but slow. They are what BepiColombo uses, and they require 8 years to reach Mercury. A crewed vehicle with nuclear electric propulsion could reduce fuel mass, but at the cost of mission duration, pushing the timeline back toward the decade-long range that is incompatible with crew health. Solar electric propulsion, which uses solar panels to power ion thrusters, is actually more effective near Mercury than at Mars, because the solar flux is much higher. Closer to the Sun means more power available per square meter of solar panel. In theory, a solar electric spacecraft near Mercury could generate substantial thrust, but ion engines, regardless of their power source, produce tiny forces. Accelerating a crewed vehicle with the mass of a habitat, life support, radiation shielding, consumables, and return propellant using ion thrust would take months of continuous firing just to achieve the necessary velocity change. The crew would be living in Mercury's radiation environment the entire time, accumulating dose, consuming supplies, and degrading physically while the engines slowly push the spacecraft toward an escape trajectory. And if a solar energetic particle event occurs during this extended departure phase, the crew has no planetary body to shelter behind and no magnetic field to hide within. They are exposed. There is another dimension to the return problem that rarely appears in popular discussions of space missions, but dominates the thinking of actual mission architects. It is called the launch window. Planets move in their orbits at different rates. Mercury completes an orbit in roughly 88 Earth days. Earth takes roughly 365 days. The relative positions of the two planets repeat on a cycle called the synodic period, which for Mercury and Earth is approximately 116 days. A favorable alignment for a return trajectory, one that minimizes delta V, only occurs at specific intervals. If the crew misses a launch window, they must wait for the next one. At Mercury, the next window comes relatively frequently compared to Mars, where the synodic period is roughly 26 months. But each window at Mercury has its own delta V cost, depending on the exact geometry, and some windows are much more expensive in fuel than others. A crew that arrives at Mercury with a fixed quantity of return propellant may find that the next affordable launch window does not open for weeks or months. During that waiting period, they continue to consume supplies, accumulate radiation dose, and subject their equipment to thermal cycling. If a systems failure occurs during the wait, if a critical component degrades beyond repair, if a radiation event damages the vehicle, the next window may become the window after that, and the one after that may be unaffordable with the remaining propellant. The mission degrades incrementally. Each passing window that cannot be used reduces the remaining options. Consumables dwindle. Systems age. The crew weakens. And Mercury continues its relentless thermal and radiation assault without pause. This is what mission planners mean when they talk about Mercury as a trap. It is not a trap in the dramatic sense of a door slamming shut. It is a trap in the systems engineering sense. Every variable pushes in the wrong direction. The fuel budget is too high. The transit time is too long, or the fuel cost is too high, with no middle ground. The environment degrades the vehicle and the crew continuously. The resources available at the destination are either absent or inaccessible. The launch windows impose timing constraints that interact with all of the above. And the rocket equation ensures that every additional kilogram of margin you try to build in costs exponentially more mass at the start. No space agency has ever published a serious crewed Mercury mission architecture. Not NASA, not ESA, not Roscosmos, not JAXA, not CNSA. The concept does not appear in roadmaps, technology development plans, or long-term exploration strategies. Mars appears in all of them. The Moon appears in all of them. Some include Venus flybys or asteroids. None include Mercury. This is not an oversight. It is a verdict rendered by the engineering community through decades of trajectory analysis and mission design. The numbers do not close. There is no known combination of propulsion technology, mission architecture, and launch capability that produces a crewed round trip to Mercury within the constraints of crew survival. The proposed robotic missions to Mercury's surface underscore this assessment through their modesty. The cancelled BepiColombo surface element and the proposed NASA Mercury lander concept described earlier represent the most ambitious surface missions anyone has been willing to consider. And both are one-way robotic packages with no return capability. Neither carries a crew, neither carries fuel for departure, neither attempts to survive longer than a brief operational window. These are not stepping stones toward a crewed program, they are endpoints. The most that the engineering community believes it can deliver to Mercury's surface, after decades of technological progress, is a small stationary instrument package on a one-way trip. The gap between that and a crewed return vehicle is not a gap that future engineering closes incrementally. It is a gap measured in orders of magnitude of mass, complexity, and mission duration. If a 10-year, one-way robotic lander is at the boundary of what the most capable space agencies consider achievable, then a crewed round trip is not merely difficult, it is in a different category entirely. The gap between a 44-kilogram one-way robotic package and a crewed return vehicle with life support, habitat, radiation shielding, surface mobility, launch capability, and return propellant is not a gap that incremental technology improvements can bridge. It is a chasm defined by fundamental physics. The delta-V requirements, the propellant mass fractions, the thermal engineering demands, and the radiation exposure limits combine into a set of constraints that no plausible near-future or even far-future technology resolves without assumptions so optimistic that they amount to science fiction. Some might suggest that the solution is not to land at all. Stay in orbit. Conduct science remotely. Avoid the surface entirely. This eliminates the landing and launch delta-V penalties, but does not eliminate the transit problem, the radiation problem, or the return delta-V problem. A crewed orbital mission to Mercury still requires getting a crew there, keeping them alive in the radiation environment for the duration of their stay, and returning them to Earth. The delta-V for a crewed orbital round trip is smaller than for a surface mission, but still far beyond what any current or near-term architecture can deliver. And the scientific justification for sending humans to orbit Mercury rather than sending increasingly capable robots is difficult to articulate. BepiColombo's 2 orbiters carry 16 instruments between them and will operate for at least a year. They do not need food. They do not need oxygen. They do not accumulate radiation damage in the way biological tissue does. They do not need to come home. The trap is structural. It is not about one missing technology or one unsolved engineering problem. It is about the convergence of every major constraint in human spaceflight: propulsion, life support, radiation protection, thermal management, consumables, logistics, mission duration, and launch windows, all pushing simultaneously against feasibility at a single destination. Mercury does not lack one solution. It lacks all of them simultaneously, and this is the realization that transforms Mercury from a difficult destination into something closer to a permanent commitment. A crew that somehow reaches Mercury through some combination of technologies that do not yet exist faces an environment that degrades their vehicle and their bodies from the moment they arrive. They face a return journey that demands fuel they almost certainly do not have. They face launch windows that may not align with their dwindling supplies. They face a radiation environment that imposes a hard timer on how long they can remain before the cumulative dose becomes lethal. And they face all of this at the bottom of the deepest gravity well in the inner solar system, on a world with no atmosphere, no accessible resources, and no infrastructure. Anyone who goes to Mercury will never come back. Not because Mercury is the deadliest place in the solar system. There are deadlier places. Not because Mercury kills instantly. It does not. But because Mercury combines just enough of every category of danger, orbital, thermal, radiative, logistical, to make the return trip collapse under the weight of compounding constraints. The mission architecture does not fail at one point. It fails everywhere, simultaneously, in ways that reinforce each other until the entire structure of a round trip becomes unsupportable. The trap does not slam shut. It tightens. Slowly, continuously, from the moment you commit to the trajectory. And by the time you arrive, the math has already decided. You are not coming home. There is a tendency in space exploration storytelling to rank danger by spectacle. Venus gets attention because its surface can crush a submarine and dissolve metal in acid rain. Jupiter gets attention because its radiation belts can deliver a lethal dose to an unshielded astronaut in minutes. Io gets attention because its surface is a churning volcanic hellscape reshaped daily by tidal forces. The Sun itself, obviously, commands respect through sheer destructive power. These destinations are dramatic. They announce their danger loudly. Nobody looks at the surface of Venus and thinks it might be manageable. Nobody proposes a crude landing on Io. The hostility is self-evident, overwhelming, and singular. Each of these places has one dominant characteristic that defines its lethality. Mercury does not work this way. Mercury's danger is not singular, and it is not loud. It is distributed, layered, and deceptive. No single factor about Mercury immediately screams impossibility in the way that Venus's surface pressure does, or Jupiter's radiation does. Mercury's surface temperature of 420 degrees Celsius on the day side is brutal, but it is not the hottest surface in the solar system. Its radiation environment is severe, but it is not the most intense. Its gravity is low, but it is not negligibly low. Its lack of atmosphere is total, but the Moon also lacks an atmosphere, and humans have walked on the Moon. Taken one at a time, Mercury's individual hazards can each be compared to something that seems at least partially addressed by existing technology or experience. And that is precisely what makes Mercury so insidious. Each comparison invites the conclusion that Mercury is manageable. Each comparison is misleading, because Mercury's true lethality is not in any single factor. It is in the combination. Venus has crushing pressure and corrosive chemistry, but reaching Venus is relatively straightforward in orbital mechanics terms, and Venus's thick atmosphere enables aerobraking that dramatically reduces fuel requirements for orbit insertion. Jupiter's radiation belts are lethal, but Jupiter sits in a region of the solar system where the Sun's gravitational influence is far weaker, and the delta-V budgets for Jupiter missions, while large, are achievable, with gravity assists on timelines that have been demonstrated repeatedly. The Moon has no atmosphere and a harsh thermal environment, but it is 3 days from Earth, within the protective envelope of Earth's magnetosphere for most of the transit. And the round-trip delta-V is modest enough that it was achievable with 1960s technology. Mercury combines the thermal extremes of an airless body close to the Sun with the radiation exposure of operating outside. Any meaningful magnetic shield, the delta-V penalties of the deepest accessible gravity well in the solar system, the impossibility of aerobraking, the absence of usable in-situ resources for propellant production, and the tyranny of transit times that are either too short for the fuel budget or too long for crew survival. No other destination stacks this many categories of difficulty simultaneously. Mars is hard, but Mars offers an atmosphere, accessible water, a manageable delta-V, and a well-studied transit architecture. Venus is hostile on the surface, but orbital missions and atmospheric probes face a far more forgiving energy budget. The Moon is harsh but close. Mercury is not the worst in any single dimension. It is uniquely bad across all dimensions at once. This distinction matters because it explains why Mercury is so poorly understood in the public imagination as a destination for human spaceflight. People intuitively judge danger by its most dramatic single expression. They hear 420 degrees and think, well, we have materials that can handle high temperatures. They hear no atmosphere and think, the Moon had no atmosphere either. They hear close to the Sun and think, surely we can shield against that. Each response addresses one layer of the problem and ignores the interactions between layers. The reality is that the thermal protection system must work while being degraded by radiation. The radiation shielding must be carried through a delta-V budget that penalizes every kilogram. The propellant must be stored through thermal cycles that no propellant management system has ever been tested against. The life support must function for a transit duration that either demands an impossible fuel load or an unacceptable radiation exposure. Every layer of the solution aggravates every other layer of the problem. And the compound result is not a difficult mission, it is an impossible one. The history of Mercury exploration illustrates this compounding effect through the story of what we have actually managed to send there. In more than 50 years of planetary exploration, humanity has sent exactly 3 missions to Mercury. 3. In the same period, we have sent dozens of missions to Mars, multiple missions to Venus, Saturn, and Jupiter, probes to Uranus, Neptune, Pluto, several comets, and multiple asteroids. The inner solar system's nearest planet has received less robotic attention than any other world except the ice giants, and even Uranus and Neptune have each received a dedicated flyby mission. Mercury's neglect is not an accident of scientific priority. It is a direct consequence of how difficult it is to get there and how demanding it is to operate once you arrive. Mariner 10 in 1973 was a flyby mission. It passed Mercury 3 times without entering orbit, photographing roughly 45% of the surface before running out of maneuvering fuel. For more than 30 years after Mariner 10, no spacecraft returned to Mercury. The gap between Mariner 10's last flyby in 1975 and Messenger's orbit insertion in 2011 was 36 years. More than a third of a century during which Mercury was visited by nothing. That gap was not for lack of interest, it was for lack of capability. The engineering challenges of reaching Mercury orbit were so severe that it took decades of advances in propulsion, materials, science, and trajectory design before a second mission was feasible. Messenger arrived in 2011 and transformed our understanding of Mercury. It mapped the entire surface. It discovered water ice in permanently shadowed polar craters. It measured the magnetic field in detail. It characterized the exosphere and identified volatile elements on the surface that challenged models of how Mercury formed. Messenger's 4 years at Mercury were scientifically extraordinary. They were also an engineering high-wire act. The spacecraft's sunshade protected it from direct solar radiation, but the reflected and radiated heat from Mercury's surface was a constant threat. Messenger's orbit was designed to minimize time over the hot day side, and even so, the thermal environment progressively degraded spacecraft systems over the course of the mission. When Messenger's fuel was finally exhausted in April of 2015, the spacecraft impacted Mercury's surface at high velocity. There was no controlled landing. There was no graceful retirement. Messenger fell into the planet it had spent 4 years studying because there was no fuel left to do anything else. BepiColombo, now approaching Mercury for orbit insertion in November of 2026, represents the most ambitious Mercury mission ever attempted. 2 orbiters, 16 instruments, 8 years of transit, 9 gravity assists, and advanced ion propulsion. Even this mission encountered problems that forced a redesign of the final approach trajectory. The thruster anomaly, discovered in 2024, demonstrated that even with the most capable technology available, operating in Mercury's environment pushes systems to their limits. BepiColombo's instruments have already returned remarkable science during its flybys. The Mercury spectrometer provided the first mid-infrared observations of Mercury's surface during the 5th flyby in December 2024, revealing mineralogical details invisible to previous instruments. During the 6th flyby in January 2025, cameras imaged permanently shadowed polar craters for the first time, including Prokofiev, Kandinsky, Tolkien, and Gordimer. The plasma environment measurements from those flybys, whose implications for radiation shielding were discussed earlier, confirmed that Mercury's magnetosphere is more energetic than models had predicted. These findings deepen our understanding of Mercury and simultaneously underscore how alien and extreme the environment is. The energetic particles detected in Mercury's magnetosphere are not a curiosity, they are a warning. They represent a radiation component that previous models did not fully account for, adding yet another layer to the radiation hazard that any crewed mission would face. Every new measurement from Mercury seems to add complexity rather than simplify the picture. The planet does not become more approachable as we learn more about it. It becomes less so. The broader trajectory of Mercury science points in a consistent direction. More data reveals more challenges. The northward magnetic field, offset described earlier, does not merely create a radiation geography problem. It reveals that Mercury's magnetosphere behaves in ways that are fundamentally less predictable than a symmetric dipole field would allow. The dynamics shift with solar wind conditions, with orbital phase, and with the planet's position relative to the Sun. For mission planning, unpredictable magnetospheric behavior translates directly into unpredictable radiation exposure. And unpredictable radiation exposure cannot be managed with fixed shielding margins. It requires adaptive responses, contingency reserves, and operational flexibility, none of which a mass-constrained, fuel-limited crewed vehicle deep in the Sun's gravity can afford to carry. MES Senja also revealed that Mercury's surface is dotted with mysterious features called hollows. These are shallow, irregularly shaped, bright depressions found in many locations across the planet. They appear fresh by geological standards and may still be actively forming. The leading hypothesis is that they are produced by the sublimation or destruction of volatile-rich material in Mercury's surface, driven by the intense solar heating and particle bombardment. Hollows suggest that Mercury's surface is not geologically static. It is actively changing, losing material to space through processes that are poorly understood. For any surface operation, actively evolving terrain introduces uncertainties about ground stability, regolith composition, and the potential release of volatile compounds that could interfere with equipment or create unexpected hazards. The cumulative portrait of Mercury, assembled from Mariner 10 through Messenger and now through BepiColombo's flybys, is of a world that is more dynamic, more complex, and more hostile than the simple mental image of a grey, cratered ball. Mercury is not the moon near the Sun. It is a distinct world, with its own active geology, its own dynamic magnetosphere, its own unique surface chemistry, and its own relationship with the Sun that is unlike anything else in the solar system. The 3-to-2 spin-orbit resonance alone makes Mercury's solar interaction fundamentally different from any other planet. The extreme orbital eccentricity, with Mercury's distance from the Sun varying between roughly 46 million and 70 million kilometers, creates seasonal variations in solar flux that compound the already extreme thermal cycling. At perihelion, the solar intensity is more than twice what it is at aphelion. Equipment designed to survive one extreme must also survive the other, and the transition between them, repeatedly, without maintenance infrastructure. This raises a question that goes beyond engineering. Why does Mercury receive so little attention in public discussions of space exploration? Mars dominates the conversation. The Moon has returned to center stage with Artemis. Venus has gained renewed interest through proposed atmospheric missions and the contested detection of phosphine. Even the outer solar system moons, Europa, Enceladus, and Titan, feature prominently in public space discourse. Mercury is absent. It is the forgotten planet, the one that gets a brief mention in solar system overviews and then disappears. The answer, paradoxically, is the same quality that makes Mercury so dangerous. Its danger is not dramatic. It does not have a single headline-grabbing characteristic that captures the public imagination. Venus has its crushing acid atmosphere. Mars has its potential for life. Europa has its subsurface ocean. Titan has its lakes of liquid methane. Mercury has a combination of moderate to severe hazards that individually sound manageable and collectively are not. The story of Mercury's danger is a story of compounding constraints, of interacting failure modes, of margins that erode simultaneously from multiple directions. It is a systems engineering story. And systems engineering stories, however terrifying they are to the people who understand them, do not make compelling headlines. Nobody writes Mercury, where multiple categories of moderate hazard interact to create an irrecoverable mission failure cascade on a magazine cover. But that is exactly what Mercury is. The neglect matters because it allows the misconception to persist. People who hear the title of this video, "Why anyone who goes to Mercury will never come back," may initially expect a simple answer. It is too hot, or it is too close to the sun, or the radiation will kill you. The truth is both more complicated and more unsettling than any single-factor explanation. The reason no one comes back from Mercury is not any one thing. It is the total architecture of the problem. It is the orbital mechanics that demand years of transit or impossible fuel loads. It is the thermal environment that degrades every system continuously. It is the radiation that accumulates in crew tissues with no adequate shielding solution. It is the absence of an atmosphere that eliminates aerobraking on arrival and aerodynamic flight during operations. It is the lack of accessible resources that prevents in situ propellant production. It is the rocket equation that penalizes every kilogram of margin exponentially. It is the launch windows that impose timing constraints on a mission already stretched beyond its limits. And it is the fact that all of these factors interact with each other, each one making every other one worse, in a cascade that has no circuit breaker. There is a concept in engineering called the design space. It refers to the set of all possible configurations of a system that satisfy the requirements. For most missions, the design space is large. There are many possible combinations of propulsion, trajectory, timing, and vehicle design that produce a viable mission. For difficult missions, the design space is small. Only a few configurations work, and they require everything to go right. For Mercury, the crude round-trip design space is, as far as any published analysis can determine, empty. There is no combination of existing or near-future technologies that produces a viable architecture. The constraints do not overlap. The requirements do not intersect. The design space has no solutions. This is what separates Mercury from Mars in the taxonomy of human exploration. Mars is hard. Its design space is small, but non-empty. Specific combinations of heavy-lift launch vehicles, nuclear propulsion, in-situ resource utilization, and mission timing produce architectures that are theoretically feasible, even if they have not yet been built. The engineering challenges are severe but bounded. Mercury's design space is not small, it is absent. The constraints are not severe but bounded. They are mutually exclusive. You cannot have a fast transit and a reasonable fuel load. You cannot have a long transit and a survivable radiation dose. You cannot have a light vehicle and adequate shielding. You cannot have a surface mission and a return capability. Every axis of the design space is blocked by a constraint that is reinforced by constraints on every other axis. Some might argue that sufficiently advanced technology could eventually open the Mercury design space. Fusion propulsion, for instance, could theoretically provide both high thrust and high specific impulse, dramatically reducing transit times and fuel masses. Advanced materials could provide better thermal protection at lower mass. Breakthroughs in radiation shielding could reduce the mass penalty of crew protection. These are not unreasonable speculations for the very long-term future of spaceflight. But they are speculations, not engineering plans. Fusion propulsion has been 20 years away for the last 60 years. Advanced radiation shielding materials that are substantially better than water or polyethylene have been proposed but not demonstrated at mission scale. And even if all of these technologies matured simultaneously, Mercury would still present the highest delta-V destination in the inner solar system, the most extreme thermal environment of any solid body, and the most intense, sustained radiation exposure of any planetary surface. Technology can reduce the magnitude of each constraint, but the fundamental architecture of the problem, the stacking of constraints across every mission phase, remains. Mercury does not become easy when technology improves. It becomes less impossible. And less impossible is not the same as feasible. There is something philosophically striking about this conclusion. Mercury is visible to the naked eye. Humans have known about it for thousands of years. Ancient civilizations tracked its rapid motion across the sky and named it after the messenger of the gods, a figure associated with speed and proximity. It appears close, it moves quickly, it seems accessible. In every culture that observed it, Mercury was a familiar presence in the sky, a planet that belonged to the near neighborhood of the Earth and the Sun. That familiarity is the deepest part of the illusion. Mercury looks like it should be reachable. It is small, so it seems simple. It is close to the Sun, so it seems like a straightforward inward journey. It has been visited by spacecraft, so it seems like a proven destination. Everything about Mercury's appearance in our sky and in our cultural history suggests that it is a place within reach, and everything about its actual physical reality says the opposite. The gap between how Mercury appears and what Mercury is represents one of the most complete failures of intuition in all of planetary science. We live in a solar system where distance is not the primary measure of difficulty. Pluto, at the far edge of the planetary system, was reached by New Horizons in 9.5 years with a relatively simple trajectory. A fast flyby, no orbit insertion, no deceleration. The mission was hard, but the hardest part was building a spacecraft light enough and a launch vehicle powerful enough to achieve the necessary velocity. The destination itself was cooperative. Pluto sits in a region where the Sun's gravitational influence is weak. Reaching it is a matter of speed, not of deceleration. Mercury is the opposite. It is close in distance, but deep in gravitational terms. The difficulty is not in crossing the space between Earth and Mercury. It is in slowing down enough to stay, surviving long enough to operate, and then climbing back out of a well that the Sun has been deepening with every kilometer you descended. Mercury's proximity to the Sun, which intuition suggests should make it easy to reach, is exactly what makes it nearly impossible to return from. The Sun's gravity is the trap. The closer you get, the harder it pulls. The harder it pulls, the more energy you need to escape. And the more energy you need, the more fuel you carry. And the more fuel you carry, the more energy you need to move it. The spiral has no bottom. The equation has no solution that a crew can survive. This is the truth that sits at the heart of this story. Mercury is not the most dramatic destination in the solar system. It is not the hottest, the coldest, the most radioactive, or the most pressurized. It is not the destination that produces the most cinematic destruction or the most visceral fear. It is the destination that produces the most complete entrapment. Every path to Mercury leads deeper into the trap. Every attempt to plan a return encounters the same compounding constraints. Every margin you build is consumed by the interactions between hazards that cannot be separated or sequenced. You cannot solve the thermal problem without mass. You cannot carry the mass without fuel. You cannot carry the fuel without time. You cannot spend the time without radiation exposure. You cannot shield against the radiation without more mass. And you are back where you started, heavier, slower, and further from a solution. Mercury is roughly 4,879 kilometers in diameter. It is smaller than Jupiter's moon Ganymede, smaller than Saturn's moon Titan. It is the smallest planet in the solar system, a world that could sit inside the Atlantic Ocean basin with room to spare. And this small, ancient, cratered world, visible to the unaided eye on a clear evening, orbiting just a few dozen million kilometers from the Sun that gives us life, may be the clearest example in all of human experience of a destination that can be seen, imagined, planned for, and reached, but never returned from. Not because it destroys you in a single dramatic moment, not because its surface is instantly lethal in one overwhelming way, but because it combines just enough of every category of difficulty: orbital, thermal, radiative, logistical, temporal, and architectural, to ensure that the sum of all those categories is greater than any vehicle, any crew, and any conceivable near-future technology can overcome. The most unsettling truth about Mercury is not that it is hostile. Many places are hostile. It is that Mercury looks like it should be within reach. It occupies a place in our sky and in our solar system that suggests accessibility. It is right there, just sunward of Venus, just inside Earth's orbit, just a short fall toward the Sun. And every word of that sentence is a lie told by intuition to a species that evolved to judge distances by walking, not by orbital mechanics. The fall toward the Sun is not short. It is the most energetically expensive journey in the inner solar system. The planet is not just sunward. It is embedded in a gravitational and radiative environment that converts every engineering margin into deficit. And being right there means nothing when there is the deepest gravity well in the planetary system between you and home. Anyone who goes to Mercury will never come back. The statement is not hyperbole. It is not drama crafted for a title. It is the conclusion that emerges from trajectory analysis, thermal modeling, radiation physics, propulsion engineering, life support logistics, and the rocket equation when they are applied honestly and simultaneously to the problem of a crewed round trip. The mission does not fail at one point. It does not collapse under one stress. It fails across every dimension at once, each failure reinforcing the others, until what remains is not a mission with acceptable risk, but a commitment with no return clause. Mercury is the trap that looks like a destination. It is the journey that looks short but costs the most. It is the smallest planet that poses the largest return problem. And it will sit there in the evening sky, small, bright, familiar, close, looking for all the world like a place you could visit, for as long as humans look upward and wonder what lies closer to the Sun. The answer is a world that answers every question except the one that matters most. How do you get home? You do not.